This is problem 76 from chapter 15. In problem 76, a ball of mass m is dropped vertically from a height h0 above the ground. If it rebounds to a height h1, determine the coefficient of restitution between the ball and the ground. So here we have the ball being dropped from rest at a height h0, then after the bounce it reaches a maximum height h1. So we want to find the coefficient of restitution, so we are going to use equation 1511 for that. And along with that, we can use the work energy formula, and we're going to do that because they give us distance before and after. So if they're giving us distance, we probably want to use the work energy formula, whereas if they give us time, we would use impulse momentum. Sometimes in a problem in chapter 15, we have to use both work energy and impulse momentum. So I think problem 76 is an exciting problem because back in physics 161, we would not have been able to predict the height that the ball would reach after the bounce, but by using the coefficient of restitution, we can figure out how high the ball will reach each time after it bounces. So we have equation 1511, which is on your equation sheet, and that is the final velocity of B minus the final velocity of A over the initial velocity of A minus the initial velocity of B. So this is during a collision. We have two things colliding. We have the ball and the floor. The floor is not moving at all. Let's call the floor object A. So for equation 1511, our coefficient of restitution is the velocity of the ball afterward minus the velocity of the floor after the collision, which is 0, divided by the velocity of the floor when the collision starts, which is 0, minus the velocity of the ball when the collision starts, which is VB1. Okay, so I need to find the velocity of the ball when the collision starts and the velocity of the ball when the collision stops. So to do this, I'm going to use conservation of energy. If I do a free body diagram of the ball while falling, then the only force acting on the ball while it's falling is the force of gravity. So if I go back to my work energy relationship here, the work done by non-conservative forces is 0 because the only force that I have is the conservative force of gravity. So I have T1 plus V1 is equal to T2 plus V2. So using conservation of energy, T1 plus V1 is equal to T2 plus V2. The only potential energy that I have in this problem is from gravity, since I do not have any springs in this problem. And we're going to go from rest when the ball is released, so that's here, to when the ball first touches the floor, which is when the collision begins. Now, in this problem here, we're going to neglect the size of the ball. So the ball is moving a distance h0. It looks kind of funny in the picture of the book because if the ball has a large diameter, then the ball's actually only going from here to here before it touches the floor. But we're going to ignore that and say the ball traveled a distance h0 before it reaches the floor. We can put our datum at the floor here and say this is when the height is equal to 0. So the initial gravitational potential energy is the mass of the ball times g times h0. The ball is released from rest, so the kinetic energy is 0. Because we put our datum at the floor, when the ball first touches the floor, the potential energy is 0. And the kinetic energy is 1/2 mv squared. Now, in my equation for the coefficient of restitution, I called the velocity of the ball when the collision begins VB1. So this would be VB1. Can we just call it V1 instead of VB1 because I only have one object that's moving? So let's call that v1 squared. Then the mass cancels out, bringing the 2 over to the other side and taking the square root gives me 2g h naught. This is v1. And this could be positive or negative when I take the square root. The ball is moving downward when the collision begins, and this is going to be important to me when I use my coefficient of restitution equation. I have to include the sign. So if downward is negative, that's a negative velocity. For my coefficient of restitution equation, I also need the velocity when the collision ends. To find the velocity when the collision ends, I'm going to use the conservation equation, but now I'm starting at the floor and going to the maximum height. So this is from when ball leaves the floor, so when the collision ends, to when it reaches the max height, h1, at this maximum height after the first bounce, the velocity is going to be equal to 0. So we have the same equation that we had before, because the force acting on the ball when it's in the air, well, now it's rising instead of falling, but you still only have the force of gravity. So you have no work done by forces other than gravity. So this is T1 plus V. Whoa. Okay, let's not call it T1 because we already said event 1 was something else. So when it leaves the floor, that would be at event 2. This is equal to T3 plus V3. Okay, so when it leaves the floor to when it reaches height 1, when it leaves the floor, its height is 0, so no gravitational potential energy. When it leaves the floor, we're looking for velocity 2 when the collision ends. So that's 1/2 mv2 squared is equal to, at the height h1, this is the turning point. This is the maximum height after the bounce. So the velocity is 0 there, plus the gravitational potential energy at a height h1 is mgh1. And so now I have, solving this the same way as I solved the equation up here, canceling out the m's, multiplying both sides by 2 and taking the square root, I get 2gh1. After the collision finishes, now the ball is moving upward, so this would be positive if this was negative. Now I can go back to my equation here for the coefficient of restitution, and I can put in what I have for VB2. That was square root of 2gh1. Then I put in VB1, which is negative, but I have a negative sign here too, so that makes it positive, square root of 2gh naught. Now, this is good because E is supposed to be somewhere between 0 and 1, so because I included the negative sign here and I had a negative sign there, this comes out to be positive. The square root of 2g in the numerator and the square root of 2g in the denominator cancel out, and then I get the square root of h1 over h naught. So now that I know the coefficient of restitution, I would like to be able to do something like this. Say my ball started off here, and I'm going to give my ball a little velocity in the y direction too, or in the x direction, so my lines aren't all on top of each other. So you drop the ball here. It goes down, hits the ground, then it bounces up to another height. I would like to be able to use this same coefficient of restitution to figure out how far the ball is going to go after the second bounce. But if you take a look at page 268, where they talked about the coefficient of restitution, and actually the figure here is what I was trying to draw. You're looking at the ball going up, reaching a height here, then bouncing again, reaching a different height, then bouncing again and reaching another height. So I would like to be able to say what the maximum height is going to be after each bounce. But if you read the paragraph on the coefficient of restitution, it says, Okay, E varies not only with the size and shape of the colliding bodies, so the size and the shape of the colliding bodies, the floor and the ball, are staying the same, but the coefficient of restitution also varies with the impact velocity. So, and you can read the rest of the paragraph, that means that just because I found the coefficient of restitution for the first bounce, it doesn't mean that I get to use the same coefficient of restitution for the second bounce. So that is something to be aware of. But if you took your ball and you measured the coefficient of restitution for different velocities, so you knew how to find the coefficient of restitution for the velocity that you had each time the ball hits the floor, then you could predict the height of the ball after the bounce. So that concludes problem 76, and we'll move on next to problem 93.